Namaskar everybody. Welcome to SDIT online classes. I am Dr. P.S. Kaushik, Principal at Sri Digambar Institute of Technology, Dosa. This is lecture number 38 on the subject engineering mechanics. In this lecture, we will be dealing with the stresses in thin cylindrical cells. As discussed in the last lecture also, the load is defined as an external force or moment acting on a machine part. Following are the four types of load. That is dead or steady load. A load is said to be dead or steady load when it is not changing its magnitude or direction. Live or variable load. A load is said to be live or variable when it is changing continuously. Suddenly applied or shock load. A load is said to be a suddenly applied or shock load when it is suddenly applied or removed. Impact load. A load is said to be an impact load when it is applied with some initial velocity or dropped from certain height. Stress in a thin cylindrical cell due to an external pressure. The analysis of stresses induced in the thin cylindrical cell are made on the following assumptions. Number 1. The effect of curvature of the cylindrical cell is neglected. The tensile stresses are uniformly distributed over the section of the walls. Third, the effect of the restraining action of the head at the end of the pressure vessel is neglected. That is, this is a head here. The effect of straining action, restraining action here of this head is neglected here. Tensile stresses are uniformly distributed over the entire section of the wall, and the effect of curvature of cylinder walls is neglected. When a thin cylindrical cell is subjected to an internal pressure, it is likely to fail in the following two ways. First is that it will burst into two troughs like this. That this is one and this is bottom one. They are getting separated at this point here. What's the other one is that it is broken into two cells. From where somewhere this is broken here. So these are the two ways that it can get separated. So it may fail along the longitudinal section, that is circumferentially splitting the cylinder into two troughs as shown in the figure here, or it may fail across the transverse section here. Longitudinally splitting the two cylinders in this cylinder into two cylindrical cells as shown here. Thus, the wall of a cylindrical cell subjected to an internal pressure has to withstand tensile stresses of following two types. That is, number 1 is circumferential or hoop stress, and longitudinal stress means if this is the cylindrical cell, if it is bursting into two troughs like this, then there will be stresses here. These are tangent to the surface of the wall, you can see. Then this is called circumferential or hoop stress. In another case, if this is the cylindrical cell, it is getting stresses like this and getting separated here. Then these stresses are longitudinal, developed here, and thus called longitudinal stress. circumferential or hoop stress. Here you can realize that the force developed due to pressure is, that is, diameter into length into pressure. This is the length and this is the diameter. This was. So D into L is the area. If P is the pressure, then this will be the force, bursting force. The resisting force will be equal to the 2 into thickness into length into sigma T1. Sigma T1 is the circumferential or hoop stress developed in this. So this gives you sigma T1 equal to bursting force upon resisting area, which gives you pressure into diameter into length upon resisting area, that is 2T into length. तो length गया तो sigma T1 comes out to be PD upon 2T. Same will be derived on the next slide. Yeah. P is the intensity of pressure, small p. D is the internal diameter of the cylindrical cell. L is the length of the cylindrical cell. T is the thickness of the cylindrical cell. Sigma T1 is the circumferential or hoop stress for the material of the cylindrical cell. We know that the total force acting on the longitudinal section along the diameter XX of the cell is equal to intensity of pressure gonna projected area. That is, projected area is P into D into T. That D into T is the projected area. D into L, sorry, not D. D into L is the projected area. Up. You can say if this is the half, bottom half, true, it will be like this. Then this is length and this is the diameter. So projected area is D into L. P is the pressure acting everywhere. Then you multiply it with pressure, it will be the total force, capital P, acting here to burst it in the two throws. The stress will be developed here, this side also, and this side also. So if T is the thickness of this and L is the length, that T plus T, that is 2T into length. So 2T into length will be the area and resisting stress will be sigma T1. So sigma T1 into 2T into L equal to D into L into P. L these should be equated, then L will cancel from both sides, then we will find sigma T1 equal to PD upon 2T. Same thing is here. This is the force, this is the bursting resistive force, equating both first and second. Sigma T1 into 2T into L equal to P into D into L, which give you T equal to PD upon sigma T1, or sigma T1 equal to P into D upon 2T. This one. Longitudinal stress. Consider a closed thin cylindrical cell subjected to an internal pressure as shown in figure A and B. A tensile stress acting in the direction of axis is called longitudinal stress. In other words, it is a tensile stress acting on the transverse or circumferential section YY. Here, this is the view. You can say that stresses will be developed here like this. The bursting force will be area of cross section pi d square into pressure P. Okay. This is the pi by 4 d square cross sectional area into P is the internal pressure. This is the bursting force. The total resisting force will be pi dt into sigma t. Realize this, that this is the cross section, its thickness is t and its circumferential length will be pi d. Hence, here the stresses will be like this, here inside. Okay, then pi d into t into sigma t2, which is equal to the bursting force, which is equal to area of cross section pi of 4 d square into pressure intensity, that is small p. So p into pi 4 d square is equal to sigma t2 into pi dt. On equating these first and second, we come to know that sigma t2 equal to pd upon 4t, or t equal to pd upon 4 sigma t. If eta is the efficiency of the circumferential joint, then T equal to PD upon 4 sigma T2 into eta C. Consider that eta C is the efficiency of circumferential joint. Okay. Some examples. A thin cylindrical pressure vessel of 1.2 meter diameter generates steam at a pressure of 1.75 Newton per millimeter square. Find the minimum wall thickness if A, the longitudinal stress does not exceed 28 megapascal, and B, the circumferential stress does not exceed 42 megapascal. Solution: given D equal to 1.2 meter, 1200 mm, P equal to 1.75 Newton per millimeter square, sigma T2 is 28 MPa, that is 28 Newton per millimeter square, sigma T1 equal to 42 MPa, that is 42 Newton per millimeter square. Okay. When the longitudinal stress sigma T1 does not exceed 28 MPa, sigma T2 does not exceed 20 MPa, we note the minimum wall thickness T equal to PD upon 4 sigma T2, which gives you T equal to 18.75, say 20 mm. When the circumferential stress sigma T1 does not exceed 42 MPa, in that case the minimum wall thickness T equal to PD upon 2 sigma T1, which gives you thickness 25 mm. Again, one more example. A thin cylindrical pressure vessel of 500 mm diameter is subjected to an internal pressure of 2 Newton per millimeter square. If the thickness of the vessel is 20 mm, find the hoop stress and longitudinal stress. Hoop means circumferential stress. So solution gives you given diameter 500 mm, P 2 Newton per millimeter square, T 20 mm. Then sigma T1 is equal to PD upon 2T, which gives you 2 into 500 upon 2 into 20, that is 25 megapascal. And longitudinal stress sigma T2 is equal to PD upon 40 equal to 2 into 500 upon 4 into 20, that is sigma T2 equal to 12.5 Newton per millimeter square, that is 12.5 megapascal. Thanks for watching this video lecture. The references were machine designed by R.S. Khurmi.